Welcome to the 6th practical session. I think today will be again very interesting, and there's also a bit of a surprise because we don't have any organizational matters to discuss today.
We can directly start with interesting topics, but maybe we mention first, Clemens is also here today and will present one of our topics. So we'll start with smart pointers, which we have seen in the lecture 4 weeks ago. So we will have some recap there and start with unique and shared pointers. And Julia will also implement a shared pointer on her own, live in the lecture hall. So this is not a very extremely complex thing, but we can do this here live. Then Clemens will talk about weak pointers. And let's see if we have enough time, then we'll also talk about lambda function as some additional topic, which is not discussed in the lecture. Okay, what were smart pointers? Maybe we try to keep it a bit interactive. Has somebody an idea what the smart pointer was? Yeah.
Like a fancy version of a pointer. It's like a wrapper where they keep track of ownership. And so, like, if it goes out of scope, it automatically frees the object that it's pointing to.
Perfectly right. Yeah, so it's like a better pointer that tracks if the pointer is still used and automatically frees then or deletes the memory if it's not used anymore. I think that's basically what I have on my slides. But now stick to the unique pointer first. What is special about the unique pointer? So we have exactly one pointer to an object. So the object is somewhere located on the heap, and exactly one pointer can point to this object. And we call this then a unique ownership. Only this pointer can access the object. And if we would allow copies, then of course this would not be very beneficial for this concept. So no copies of this pointer are possible. And maybe here in the code, how to do this. First, remember for the smart pointers, we need to include memory as a library. We specify the smart pointer type. Then what type the object is where we point to. And then we also had this fancy function here, which we called make unique. So this creates then a unique pointer object, which can be passed to the constructor of the pointer. And then we can use it like an ordinary pointer, so we can also dereference it here.
Maybe a bit of a tricky question. Now we have this unique pointer, and we can only ever have one pointer to this object on the heap. Why should we use a unique pointer? Because I think in C most often when we used pointers, we had multiple pointers to one thing on the stack or on the heap, and that was their purpose. So why can this unique pointer now be something we want to use?
So basically, with the methods that we learn in this lecture, a unique pointer is not very useful because really we can only have one pointer pointing to it. And if we want to do a bit more with the unique pointer, maybe we want to pass the unique pointer to a function, or let's be concrete. Let's assume we have a card in a game that can only exist once. So unique pointer would be a nice choice. And now the problem is if we want to pass it to a function or we want to print it or anything like that, we always need to copy the pointer somewhere. And then unique pointer doesn't work. It would only work if we could kind of move this pointer around so that maybe you have the card, you have the ownership of the card, and then you move it to my cards, and now I have the ownership. This is possible in C++, but we don't learn it. So maybe the unique pointer is not really useful for us. So we would have rather a shared pointer between us then.
Yeah, I think we saw it in the lecture, though, how you could move a unique pointer around.
Yeah.
Like the thing is with the, maybe let's get back to the difference when we talked about shared pointers.
Yeah.
Yeah.
But also in the lecture it was presented that we can kind of still copy a unique pointer in some way was presented there. And I want to demonstrate that this doesn't work. And they fixed it on the slides already, but let's see. We create some unique pointer of type integer, my pointer. Now we learned, okay, we need to use standard make unique, also specify the type, and then some value. Let's put 1. So this 1 is then the value which is stored in the integer where the unique pointer points to, and I need to include memory. And forget about the student class who will use this later. So we just have the main here. Okay, so make unique. And now if I would kind of directly say, let's create a second pointer, copy maybe, and try to copy the pointer. This doesn't work, yeah, expected, we cannot copy a unique pointer. But let's trick it a bit, yeah? We learned in the lecture that if we call my pointer get, then this returns the raw pointer. So the integer pointer that we're used to in C.
Yeah, so this is actually the pointer, this unique pointer stores internally where our object is on the heap.
So this is actually the address of the integer where 1 is stored then. So maybe, yeah, let's say integer raw, integer pointer, raw pointer. Okay. Let's give it one more try. Now pass the raw pointer. Well, it seems good. Doesn't complain.
So this works because instead of make unique and make shared that you saw in the lecture, we can also just allocate something on the heap on our own and then pass it to a shared or unique pointer. And then after this point, this shared or unique pointer will manage the object that we allocated on the heap. But what we here do is we didn't actually allocate something, we just passed this pointer that is already managed by the first unique pointer to the second one.
So 2 unique pointer objects pointing to the same memory location. It compiles, yeah. But what could be the problem now if I run it? We see double free. And this is very logical because this unique pointer thinks, yeah, I'm the only pointer pointing to this integer 1 here. And if I go out of scope at the end of the main function, I can free the memory. And also the second unique pointer thinks, I'm the only pointer that points to the integer with the value 1. So I can free it if we leave the main function, but then we free twice. Yeah, so this doesn't work.
Yeah. So somehow this unique pointer, because it's unique, of course it always assumes that it's the only pointer to this heap object. And then of course it will always free it when it thinks it's the last pointer going out of scope.
So we cannot copy a unique pointer. We also have it on the slide. But now we move to something better, to the shared pointer. Now this is all not a problem. Now we can have multiple pointers that point to the same object. And now this is also called a shared ownership. And of course, they need to be kind of aware that there are other pointers pointing to the same memory location. So they need to store this somewhere. And when we implement the shared pointer later on our own, we will see how to do this. And of course, in this case, copies are possible. And yeah, what changes is we always write shared instead of unique. So if we create an object, we write shared pointer. If we want to initialize it, we use make shared and not make unique. We can now copy the object. So this is then no problem anymore because shared pointer, multiple instances can point to the same memory location. So this is the change here. And maybe we want to put this now in a bit more action. So,
just to compare this now to the unique pointer.
Yeah.
Now we had this example before that what happens if we pass a unique pointer to a function, then we would somehow, because everything is copied that we pass to a function, we would somehow need to either give up our ownership and give the ownership to this function, or we just somehow can't do it. With the shared pointer now, this is not a problem because we can have two shared pointers referencing the same heap object at the same time. So we can keep a pointer to this heap object and we can copy the shared pointer to a function, and then this function can have a pointer to the heap object, and it's no problem because we can have multiple references to this heap object in contrast to the unique pointer where we only ever have one.
So we can directly test this now. So let's get rid of this unique pointer stuff here. I just want to briefly explain what I've prepared. So we have a class student which has a name, a matriculation number, a constructor which sets the name and the matriculation number, and toGetter for the name and the matriculation number. So very basic, nothing special. And now we can also see that we can create shared pointers to our own classes. So we could, for example, create a shared pointer of the type student now. Let's create me. And we use make shared for this of type student. And I pass now my name, Michi, and maybe some matriculation number here. And why doesn't it So make shared is a function, so we cannot use the brace initialization. You will use the normal parentheses here. Okay, so now I already exist, and now I want to write a function that prints me, basically. So, I don't know, print student, shouldn't return anything, takes as a parameter a shared pointer, and let's call it just student, and maybe print this is a student. Now we're on a student here, get name. Okay, now it doesn't work because we have a shared pointer with dereference. Yeah, same as ordinary pointers. We use now the error to access attributes and methods. And yeah, this should suffice probably. Okay, let's try this. And I should call it, of course. So print student with myself. And okay, I can print myself. And I want to add a bit now, because now shared pointer, it would be interesting now how many shared pointers point to me. Yeah. So maybe is referenced by, and now there's some pretty thing here. So let's print by how many shared pointers I'm referenced. And we can do this by taking student. Now we do not dereference here to get to the object, which is behind the pointer, but we really want to get to a method of the shared pointer. So we use the dot. And now use count exists. So now we can print how many shared pointers point at this moment to the element which is behind, so to me, basically. So now we have the Michi here. We pass it to the function, print it here. How often is it referenced? 2 times. Okay, let's see. Is referenced by 2 shared pointers. Yeah. So why? Because one is in the function. This is a copy of the object here. And this is not possible with unique pointers because it's referenced 2 times. So we cannot put the unique pointer here.
Maybe just to reiterate. So this arrow, as you know from C, first dereferences the object on the left and then calls some function or tries to get an attribute from that object. Therefore, when we use this arrow here, we have this shared pointer, and with the arrow, we actually access the student pointer or the student that is on the heap. And with this dot here, we do not get to the student, but just access something that's on the shared pointer class.
One more thing, what if I add here a reference? Print student, and now I have a shared pointer reference here. What would be printed now in terms of how many references are there to me? Yeah? 1? Okay, let's try. Yeah, of course, correct. Yeah, because now this shared pointer is just a reference of the first one, so no copying was done. So actually, this would be possible with unique pointers, because now we still have just one shared pointer or then one unique pointer pointing to the student. This would be possible.
But
Yeah?
please don't really do this, because what we want to do with the shared pointer is to ensure that we can always access the heap object and that it's not freed like before we want to use it. Because this shared pointer ensures this, because as long as we have a shared pointer, we know that it's not been freed yet. But now if we take a reference or a pointer to a shared pointer, so a normal pointer, not a smart pointer, then of course this variable that we are referencing or pointing to could already have gone out of scope or be deleted, and then also the heap object that we might want to access is gone. So somehow if you do this reference to a shared pointer or unique pointer, we are losing a bit the reason why we're actually using the smart pointers.
Yeah, so it doesn't really make sense to use it then. I want to keep it now here because I don't want that it's counted, this shared pointer is counted, because I want to continue in the main for a few more things. Yeah. So maybe what we can also do, just to demonstrate this, we can also write a function which returns a shared pointer. So we could just return a shared pointer of the student from a function, and maybe we create Clemens and make a shared pointer of type student, call it Clemens, of student, maybe some other matriculation number. So we can create the Clemens here, and then we return him from the function. And now we could also have here a shared pointer, which is Clemens, and which we obtain by calling the create Clemens function. And also this works. And then we can maybe print Clemens here.
So why are you here doing the assignment operator?
I can also do it like this, doesn't matter, it's the same. So we can also initialize a shared pointer based on the return value of some function. Now if I print Clemens here, and I still have the reference here, so this shared pointer here doesn't count, how often does Clemens exist if I print it here? Once or twice? Once. Right, you say once, let's try. Yeah, it exists just once, because here it existed once, then here it was copied to this shared pointer here. So very briefly it existed 2 times, but then this function terminated, and then the one reference is gone again, so it's just reference once. Maybe I can do something different now. Maybe I take a vector of shared pointers of students. I don't know, student list, and put in Michi Clemens. I also need to include the vector somewhere. How often do I now exist here? Mm-hmm. 2 times, yeah, let's see. So now I exist 2 times because one shared pointer is on the stack here and one is in the vector stored. Okay, do I have something more here? Yeah, maybe we can also, of course, print all students, where we pass in the student list, and print all students. Now I'm a bit lazy. These types get really long if you use shared pointers. No, I don't want to print them actually, but let's print student, student list at 0. I think this is the last experiment that we make here.
And DS.
Hmm?
DS.
All students. Yeah, okay. So if I print student at 0, then this should be me. How often do I exist here now? Yeah, 3 times. Yeah, okay. Okay, now we have 3 shared pointers. This vector is a copy of the original one. So we have 2 times 1 on the stack. So now I'm 3 times there. I think you got it, how this works. And the important thing is, now if I print it again after the print all students function, then of course I only exist twice. Because this function terminated again, the copy of the vector was deleted, and just the vector and the original object exist with 2 shared pointers. Yeah. And very nice, I didn't have to free anything here in the example. We can also test it with Valgrind if you like. Then if we monitor this, we have 6 allocations, 6 frees, 0 errors. So we do not need to think about memory handling anymore. Okay, I think that's all I wanted to do. Now, your part. I should have cleaned up a bit my mess.
Okay, so what we want to do now is implement some smart pointers of our own to really see how they work. And maybe if you know how they work, you really get a better understanding and maybe are not that afraid to use them. Maybe let's start with the unique pointer, because the unique pointer is implemented in a way, I think it's just implemented like any class which holds some dynamic memory. Yeah, but let's try. We'll start with the unique pointer. And what we want to do is, this pointer should reference or represent a pointer to a student. That's why I kept the class here. So, of course, I need a student pointer, which this unique pointer represents. So, as we can see, our unique pointer is just a wrapper around an actual pointer where we keep track and make sure that the memory is freed. So, what do we need? Well, a constructor. Maybe, yeah. I think you have the name and the matriculation number. Something like this. And then what do we want to initialize? Well, just this pointer here. And I won't do anything like make shared or something, or implement something like that we know from normal pointers, because normal smart pointers work with any kind of types, but it's a bit too complicated now, so we'll just do the student, and then I know what parameters I need to construct the student, and then directly construct the student here on the heap.
And the new creates now a raw pointer again.
Yeah. So if you can remember, this just allocates a student on the heap, And if we have this new, we also need some to delete it. So I'll create this destructor. And what do we need to do? Well, we need to delete the pointer.
Should I ask now? What do we need to do now immediately?
Yes. Yes, delete the copy constructor. Because we have something which is on the heap, we need to implement the destructor to actually free this memory. And always when we implement the destructor, we also need to implement the copy constructor. And also something that you didn't learn yet, but you need to think about.
Which we will see in the lecture today later on. So why don't we implement the copy constructor now? Why want we to delete it? Yeah?
Yeah, maybe a question.
Why do we delete the copy constructor and not implemented it now? Because, I mean, we could do that. We have learned that.
Mm-hmm.
Yeah, exactly.
Yes, because it's a unique pointer. It wouldn't make much sense to implement now some copy constructor for something that we do not want to be copied, because that's the point of the unique pointer. Yeah, maybe try it out. So I have this unique pointer I can create now, which is just for students. So I'll create you again.
Mm-hmm.
Something like this. And let's hope that we do not have any memory leaks if we try this out now. Yes, this is fine. So up until now, this unique pointer is just very basic. I mean, this is just what we did all the time when we wanted to implement some memory on the heap for any class. Just now we called it unique pointer. Yeah, maybe let's also try to use it.
Yeah, it would be nice that we can kind of access the pointer somehow.
So I will just create a method to dereference this pointer. And I'll return a reference because they're nicer to use than pointers. So something like this. I'll just return this reference, and now we can call, because if you see now, if I do this dot here now, I'll access the unique pointer, and which I cannot get anything from the student from, but I wrote this dereference here, where I then can access the get name. And this is very similar.
Intline.
Oh. This is very similar to what we saw with the unique pointer that we got from the standard library, because if you replace this deref with the error operator, then it's basically the same.
How to do this? Today's lecture. Yeah? So we haven't learned how we can overload operators, but basically this dereferencing can be replaced with the error if we write the function correctly.
Yeah, I think we can show this next time then.
Yeah.
Okay, so this works. We do not have any memory leaks. Maybe just to show this again, if I want to make some method out of this now, then of course this will not work. Oops, no, student. Because I deleted the copy constructor. So this behaves very similar to the unique pointer we already know.
Maybe show the error message, but it should basically say call to deleted constructor of unique pointer in red here, so this doesn't work. But now, would it be nice if you can make it happen to work?
Yeah, that would be nice. Maybe I'll just show this quickly. If I would not do this,
so you remove the deletion of the copy constructor,
then okay, now it's a segmentation fault. Yeah, but I think it's a double free, right?
Yeah, but in the case of a double free, it's probably not said what's happening, so it can happen anything. So in this case, segmentation fault happened here.
Yeah, but it does not work, same as with the unique pointer. So maybe change this to a reference, so we compile again.
So we cheat around again, but this works, but it's a bit awkward to reference the unique pointer now.
Yeah, so I think we tested everything that you tested as well, and our unique pointer behaves very similarly to the one that we get from the library. So maybe let's try to implement a shared pointer. Maybe should I just...
Yeah, just re-implement it here directly.
So I rename this unique pointer to a shared pointer.
Are we done then? Unfortunately not. Copy constructor.
I don't know why your indentation now.
I don't know either.
Yeah. Maybe just replace it here and here. And our goal would be now that we can use the shared pointer like this.
Yeah? Okay.
So what's stopping us from just implementing a copy constructor for the shared pointer? Because that's everything that's missing, so that we'll be able to copy this pointer around. But now in here, we somehow need some case distinction, because we know if this is the last, more or less in the destructor and in the copy constructor, because if we just do something like this, that we set our pointer to the pointer from the other object, then okay. Now, if we copy this now, we have two shared pointer objects which do a shallow copy and both reference the same student object on the heap. Because I just copied the pointer here, not the actual student object. But this will cause problems because this is the same as if I would just implement.
Let me close the Discord briefly before you see everything. Huh?
Now the same thing happens as when we delete the copy constructor, because this is just what the default copy constructor does. So somehow we do not want to actually delete the pointer, the object on the heap, in the destruct of the shared pointer here, if we are not the last shared pointer referencing this heap object. So this is somehow a tricky task to come up with something now, because we need to know if we're the last shared pointer referencing this student. Does any one of you have an idea how we could implement this? Yes?
I think we should initialize like the red counter for the shared pointer, and then the red counter reaches 0, then the destructor will be triggered.
Okay, so we saw this with the shared pointer from the library. It somehow has a reference counter. And we need something like this as well, so where we can count how many shared pointers are referencing our object.
So let's create some integer reference count.
Or just reference count.
Maybe in the constructor, set it to 1.
Then here we somehow need to increase
it.
it.
Increase it by 1. And in the destructor, decrease it.
Yeah, so we first check, or let's first decrease the reference counter. Oops, reference count. And then if it is 0, then we want to delete this. Does this work now?
Who thinks this works? Raise your hand. And who thinks, yeah, okay, wait, who thinks, yeah, 2 people, yeah. Who thinks it doesn't work? Also 2 people. Yeah.
Those who think it doesn't work, do you have any idea why it doesn't work? Yes. So here we just increase the reference count of the copied shared pointer that we are just creating. We know there exists this other shared pointer, but we only increase the ref count of the second one.
So basically, if we do 1 copy, we have 1 shared pointer, so the original one, which has reference count 1, and the other shared pointer, which also has a reference count variable, which is then not even copied, I think. But only the second one is increased if it would have been copied.
Yeah, we would need to initialize it with 0 here.
Yeah, but then the reference counts don't match.
And I mean, so maybe you might think now, okay, then let's just also increase the reference count of this other object. So do something like this here. But what happens now? I mean, it's constant, so we can't do this.
Yeah, but okay.
What happens now if we copy it for a 3rd time? Then how would we increase the reference count of the first pointer? Maybe I should draw this on the blackboard.
If you like. I will get you some light.
So I need to. So just very quickly, if this is our first shared pointer, we initialize the reference count to 1. Now we copy it, and we increase of this one, and we also know the original one, and increase the reference count to 2. Now still everything is fine. What happens now if we delete this one here? Well, then we would decrease here to 1. But this reference count is now wrong. So this wouldn't work. Also, if we copy this a 3rd time, we could update this here to 3, but we have no way of updating this one to 3. And now they somehow never decrease the reference count because we can't decrease this one here, so this will never 3.
So basically, we would need some reference count which is shared among all objects.
Yeah. Does anyone have an idea how we could do a reference count which is shared among all of our shared pointers? Yes? Static would be an idea, and this would work in our case here. But what happens if we have 2 students? So we have student 1 and student 2. Both of them have multiple shared pointers referencing them. And a static variable in a class, there's only 1 instance per class. So both of them would have the same reference count, which would not be nice.
So we need a different solution here.
Yes?
Make the ref count a pointer.
Yes. So, very good. Make the reference count also a pointer and also store it on the heap. So, if we do something like this, we have this reference count on the heap now. If we are copied, we just copy the reference count of the other object.
So this again means copying the pointer, so making a shallow copy.
This is a pointer here. And now we can increase this reference count. Maybe I'll just put parentheses around it so you get what's happening. We actually increase the reference count that is on the heap pointed to the reference count. So now this would also work if we have 2 separate students and create shared pointers to them, because now both would have separate reference counts on the heap. Now, of course, we also need to dereference here in a destructor, and also here dereference when comparing to 0.
Looks good.
Here, we also need to delete the ref count.
Yeah, because now both are on the heap. Yeah. Let's see whether
Let's
this
try.
works. Yeah.
Okay, it does not crash. Let's try with Valgrind.
Maybe scroll up a bit for the freeze and allocations. Wow.
Yeah.
4 allocs, 4 freeze. Looks rather good. Maybe can you copy me for the third time?
Something like this. Wait, I'll do it like this. So explicitly calling the copy constructor. Yeah. No. Yeah, also works.
And also, again, we have 4 allocs for freeze because no copy of the memory was done. Maybe,
Yeah, maybe this is what I meant. So this is what I meant with, now in this situation, a static variable would not work. I mean, we can check that our solution works. Yeah, 6 allocation, 6 freeze, so seems to work. But here, so if we just have u as a shared pointer, then this static allocation would work. But as soon as we create really a new student on the heap and want to have shared pointers to this student, then the static variable would fail us because then we only have one static variable for all shared pointers.
so maybe make this explicit. As maybe we have not talked so much about static variables, so this would mean we write here static integer ref count. I have the wrong keyboard layout. And then this ref count would be the same for all objects of shared pointer. So in particular, it would be the same for me and for you. So we would have, but we would need to store here a 2 for me and a 1 for you. And this is just one variable which can only have one value, so this doesn't work. So it really needs to be on the heap somewhere. Just to make this explicit a bit more. Yeah?
I mean, of course, you can find some workarounds where you do like store some map as a static variable where you store the reference counts, but I think this is the easiest solution.
And this works. Yeah? Very nice, and I think it's not so complicated. Because basically, increase the reference count in the copy constructor, decrease it in the destructor, and if we're the last, then do the cleanup stuff. And that's everything. There's no more magic behind that.
Yeah, and this is also how shared pointers work. Not exactly how they work, but very similar to these shared pointers from the library also work. So, yeah, I hope this cleared up a bit how these shared pointers work, and that this is not just some magic that somehow automatically frees everything, but this is really, it just keeps track of how many objects do exist, and then if there are no more left, it frees them. And we can easily implement this on our own. Maybe to reveal something for the next practicals, today in the lecture, you will see how we can implement and change operators for our own classes. And then next time, maybe we can show you how we could do something like actually how it's done in the library. So something that we can do something like this. Okay. Then
Perfect. Does it work? Nice. All right. We will now talk a bit about weak pointers. And in order to show you why we need weak pointers, I have constructed a small example. It's a game where we basically have two classes, one manager and 3 players. The manager holds a reference to each of the 3 players, while the players hold a reference back to the manager, and each player has an opponent, and players can fight against each other, and the fights are only decided by which player has more power, and power is only an integer.
So you can imagine this like something you would create in some game, like where we want some central manager which really knows what players do we have, but we also want the player to know to which manager this player belongs, and also which other opponents do exist.
Exactly. And to maybe make it a little bit more clear, I have a visual representation. Basically, the manager is saved on the stack, or it's not saved on the stack, you will see in a moment. But the manager has a reference to the players, and the players each hold a reference back to the manager. And then player 1 has a reference to player 3, because that's their opponent. Player 3 holds 1 to player 2, and player 2 holds 1 to player 1. So each player fights against each other player exactly once. So let's take a look at it in code. As I said, the player has 2 references and a power. The manager has 3 references to each of the 3 players.
Yeah, and we just implemented some setters here. So again, like the student class, nothing special.
Exactly, and the game manager also constructs the 3 players when he gets constructed.
Yeah, so now really on the heap without any smart pointers.
Exactly, so for now we only use raw pointers. And then here we only have 2 setters for the player. Then we have a fight function where we just compare the power and print which player has more. And then in the main function, we basically construct the game manager, as I said, as a raw pointer for now. Then we set the manager in each of the 3 players. We set the opponents so that each player has the right opponent, and then we have them fight, and then we delete the manager.
If we just go over this and compare it to the visuals, the game manager created the players. So obviously the manager has some pointer to the player, and then if you go to the code with the set manager, we set the manager for the player. So now the player also has a pointer to the manager, and the same here down here for the opponents, where we just set for player 1 opponent player 3, player 2 player 1, and player 3 player 2, which is exactly just like from the visualization.
Exactly. So I would say let's maybe try it out. So let's first compile it and run it. And we see the players are created, the manager also, but for some reason the manager gets destroyed, but the players don't. And if we take a look at the .hbb, we see we should have probably deleted the players.
Yeah, so we just have these debug statements in all these structures, just pretend that we do something important in those. But yeah, we somehow see that the debug statements in the players are never called.
Exactly. Maybe that I should have explained earlier, but these debug statements help us visualize when a class is destroyed or created. And we can also run it with well-grind and see that we are really leaking memory here. So obviously. But I learned that apparently shared pointers manage the memory for me. So if I use shared pointers, then I don't have to worry about deleting them. So I decide on just using them. So for that we have to include memory. And then we just change everything to a shared pointer. And you also need to change it in the CPP, of course. And then we also need to create it as a shared pointer here. You can also construct shared pointers like this. Then I also need, of course, I don't need to delete the manager manually in this case. And I also want to have the players as shared pointers.
Yeah. So luckily for us, the compiler tells us if we forgot somewhere to change the pointer to a shared pointer.
Obviously, this is not the best way of doing it, but it's just for an example. You should probably use, and firstly, they shouldn't be public, and there also should probably be an array or a vector. So let's see. Let's see if we forgot it anywhere. Does it compile? Perfect. Now let's execute it. Not with Valgrind, maybe at first. Okay, I should maybe also actually delete the Valgrind part. Now we see that for some reason, the manager and the players don't get destroyed, which is weird because I thought that shared pointers manage the memory for me.
Yeah, so up until now, what Michi showed us is that every time we use a shared pointer, it just works. It always frees stuff for us. So apparently they don't just work.
Yeah, so let's maybe investigate what happens
Yeah.
here. I will first go through step by step, and I have also a visual representation. So at first we create a game manager. There. So we are on the stack, we create the game manager, we have that reference on the stack here. The game manager then creates the players. The players then get the manager as a shared pointer, so they reference back the manager.
And now, yeah.
The reference counter first is 1 because of the shared pointer on the stack. Then the player gets a reference to the game manager, so this reference counter increases to 2, or in our case 4 because there are 3 players, but in this example it's 2.
Yeah, so we can actually just count the arrows that
Exactly.
we have here with the shared pointers, because we can see, okay, in the main we have a pointer to the game manager, and from the player we have a pointer to the game manager, so there are 2. And the shared pointer just actually count this for us.
Yes, but does maybe someone see a problem here?
So why doesn't this work now, that if we terminate the program, everything is freed automatically? Yes?
Because the manager and the players have pointers of each other, it's always that one party is not freed because it lives longer than the other one.
Yeah, kind of. I think you meant the correct thing, because we need, this basically is the reference that the rest of the program has to our game manager right now. So then our program executes, and at the end we basically leave the local scope. In this case, this means the program terminates, but this could be any function, so let's just say we leave the local scope. Now this shared pointer gets deleted. So this reference gets deleted. The reference counter decreases by 1, but the reference counter still hasn't reached 0. And the rest of the program has no way now of knowing that this memory even still exists or where it is, because we just deleted the last reference to it that we had. So in other words, the game manager and the player are keeping each other alive without the rest of the program knowing about them anymore.
Yeah, because the player somehow thinks, oh, I can't delete myself yet because the game manager has a reference to me. And the game manager thinks, well, I can't delete myself either because the player just has a reference to me. And the shared pointer always ensures that as long as we have a reference, our memory is never deleted. So somehow this is an issue now.
That's what is often called a circular reference. And I think maybe the best way of explaining it is through the lens of ownership. Basically, we have learned that a shared pointer basically implies that I own that object. And in this context, owning an object means that as long as the owner is alive or owners are alive, the object that is being owned doesn't get deleted. But the problem now is that the manager obviously owns the player, but the player also, again, owns the manager back. So in other words, the manager owns itself indirectly, and so does the player, which in this case means that they keep each other alive. And whenever you have objects that basically own themselves in this way, this will always lead to problems like this. Because, I mean, if you're lucky, this chain could get disrupted earlier, but obviously when we for example, if this reference gets deleted before this reference, but obviously we don't want to rely on luck when we code. So this is something that's very bad if an object owns itself. Yeah, so what is the solution? Well, as you might have guessed, it's the so-called weak pointer. A weak pointer is basically a non-owning reference that doesn't increase the reference count. Therefore, a weak pointer does not keep the object it points to from being deleted. We can very easily initialize or make a weak pointer from a shared pointer. So I would say let's make one of the references a weak pointer, because we basically want to ensure that they don't own each other, so one of them needs to be weak. And I think it makes a lot more sense in this case for the game manager to own the player, because the game manager makes the player, so it wouldn't even work the other way around.
Yeah. Maybe you can also think about the weak pointer as just a normal pointer, which does not affect the reference count of the shared pointer at all. And as long as one shared pointer in this loop is a weak pointer, then we should be fine, because then one reference count is not 2, but 1, and then this gets deleted.
Exactly. So I would say let's maybe try this again and see what happens. Okay, so now the manager is getting destroyed.
So this seemed to work.
This seemed to work, yes, but for some reason the players still aren't getting destroyed in this case. But maybe with the knowledge that we just learned, can we find out what the problem here might still be? Where else could there be a circular reference in this code?
Yeah. So does anyone have an idea why? So it works now for the game manager. We changed this to a weak pointer. Why doesn't it work for the players? Why are the players not deleted? Yes?
Maybe because of their own circular fighting.
Yes.
Exactly.
Because they are fighting each other in some circular manner. Yeah, maybe you can show the visualization for that.
The opponent is also a shared pointer. So the opponent reference is also an owning reference in this case. And if you look at it visually, we first have the game manager who creates all the players. So the ref count is now 1. Now we set the opponents in the players, meaning that player 1 now owns player 3, player 3, player 2, and player 2, player 1. And in this case, we can again see that there's self-ownership going on, because obviously over more curves this time, but player 1 still owns itself, and player 3 and player 2 too.
Yeah, because player 1 owns player 3, player 3 owns player 2, and player 2 owns player 1. So again, we have this player 1 owns itself somehow.
Exactly. And now if the game manager gets deleted, of course, the reference count now is 1 instead of 0. So they are also not getting deleted in this case. Therefore, we also need to make these references weak so that this can't happen.
Yeah. So it would already be enough if one of those 3 is weak pointers. But of course, because the game manager owns all the players and the players do not own each other, which would be kind of a weird concept. We already have the game manager, which knows all the players, so maybe we can just make all of them weak pointers.
The problem now is that this doesn't work. The thing is that, as I said, weak pointers aren't owning. So if I have a weak pointer to an object, I don't keep that object from being deleted. Which is very bad, because there's nothing that keeps this object from being deleted while I work on it. Because if, for example, the game manager somehow gets deleted while I am here, suddenly this pointer points to nothing anymore.
Yeah, so because the pointer is weak, if we want to access the memory that this pointer references, we can't really know, did the shared pointer already delete this memory or not? Because we did not influence the reference count. The shared pointer could have already deleted the memory that was on the heap, and we still have a weak pointer to it.
So there is a solution to this, as you might have guessed, which is the so-called log function. What does log do? Log basically returns us a shared pointer from the weak pointer. This means that in our case, we then own the object again. I will maybe show it to you in code. So we can make a shared pointer to a player, opponent, from opponent, log. So this basically now makes a shared pointer again from the opponent. And because that shared pointer is saved on a stack, this shared pointer is not owned by any objects, but by the local scope. Because of that, it's a temporary ownership. So as soon as we leave the scope, the shared pointer is, we don't own it anymore. But while we are here, we do own it. So while we are in this function, there is no way of getting it deleted, because the reference count can never reach 0 in this case.
Yeah. So this opponent with the underscore here is the weak pointer that we stored in the class, and the opponent without the underscore now is the shared pointer, which we somehow, the weak pointer, we somehow promoted to the shared pointer. Because, and this will not cause problems, will not create a loop, because we just do this for a very short time.
Yeah, because no one can really own the stack in this sense, right? In the same sense that we can own an object.
Because we know that when the players fight each other, at some point they will be done fighting. And we know that we'll be done fighting when we terminate the program. So we know this shared pointers will again be weak pointers, and everything will be freed when we terminate.
Exactly. And another good thing about this log function is that it also checks if the shared object, if the object that the weak pointer points to has expired or not, if it already has been deleted. And if it has been deleted, it will return us a shared pointer that points to null. So we can very easily check if the object has already expired. And in this case, we do this here. And if the object already has expired, because the game manager, for example, in this case was deleted somehow when we called the fight function, then we would return immediately and not use that pointer. Yeah, and as you already explained, since it is on a stack, there's no way for it to cause circular ownerships in any way.
Yeah, maybe some way to interpret this, if we really have this game manager now, and we start to fight a player. So we choose a player, we go into the fight method, and then, for example, the player leaves the game and the game manager frees the memory of the player, then this would not be a problem, because we just have a weak pointer to our opponent, and if we try to get a shared pointer from it, we'll get a null pointer and know, okay, this player does not exist anymore, and we can't fight that player.
Exactly. If there are no further questions, I would give it back to Michael, but all right.
Yeah, and I know this with the weak pointers and the circular dependencies can be a bit much at the beginning. To really understand what's happening, maybe you can afterwards look at these very nice visualizations again if you're somehow confused, and really try to think about how did we implement the shared pointer, and what would happen if we construct something like this with our shared pointer, what would happen with the reference counts, and maybe write them down again. So how would they be influenced? And then I think it's, then you think you can understand it.
Here we are. back in the business. Move to the right. Doesn't work.
So do you still want to do the last?
8 minutes left. Let's
We-
start with it.
Yeah, we can start.
So this is something new, which you haven't seen before in the lecture. Maybe you know this concept from, for example, Python. There also lambda functions exist. And yeah, the next slide will be really unrewarding because I haven't put so much on it. Just one statement here. They're kind of anonymous functions. And I put on the syntax of them.
Yeah. So maybe think like function pointers in C, but without ever really giving the function a name and writing it down somewhere.
But basically what we see here, captures, what is that? I don't know. Parameters, okay, we know what parameters in the function are. Specifications, okay, yeah, this could be, for example, no except. I think that's the only that we have seen so far.
Const.
Yeah, but const in the context of functions is not very useful.
Yeah, okay.
Then we have a return type. Okay, this is then followed by some arrow symbol here. Yeah, okay. And then the function body here. And now I'll skip to the first example. So this is an ordinary function. Yeah, so print student, I think we've seen this kind of today, where we have a return value, of course, yeah, then we have some parameters here, or one parameter here, and then we have a function body. Okay, yeah, you're very used to that. Now put this into a lambda function.
Yeah, so what do we want to do? We somehow do not want this function to just have it as a function, but we want to store it somehow in a variable, like a function pointer in C. So let's try to do it with the syntax you showed us.
Yeah, first, notably, now the function, or what we say that this is a function, is contained inside of the main. Before, we have all the functions outside of the main, but now really it's inside of the main.
And it looks very much like a variable because we also have this auto here that we know from C++, which automatically determines the type of a variable.
And then it's stored in this variable, yeah. And then we have the captures. Okay, they are empty. We probably do not come to them today. Then we have the parameters. Yeah, same parameter as before, here above. Then we have the return value, same as before. Yeah. And then we have the function body. And in the function body, the same is happening as before.
Yeah. Maybe you can show us how you call it, how you would call this function.
Yeah, we can do this. We can just take the print student lambda and call it with the correct student, which we have not created here, but we would just call it as an ordinary function.
Yeah.
This is the name, basically.
So it really behaves like a function, but as a variable. Maybe something a bit tricky. Now we wrote here auto. What would be the type of this function that we have here?
Don't ask me that. Now it's such a type is quite complicated because it needs to incorporate the parameters, the return type, also the captures here, if there are any. So usually we don't want to write explicitly the type of lambda functions, but we just write auto in front of them and say, this is enough.
Yeah, you have to write auto. You can spell out the type of lambda functions. So because somehow these are weird types, we need the type is somehow the parameters, return value. Yeah.
Maybe, I hope I can copy it now directly from here. Let's try a bit around with that. Now we have here the shared pointer. So, oh no, we can please remove the main. Remove the main function, replace it with the one from before. Get rid of the shared pointer. We don't have this yet. Just copy it over. Maybe we want to do something. Now we want to implement, put it now a real function, yeah, so an ordinary function as you used to use, which takes two parameters, a vector of students, so a list of students, and a lambda function, which is applied to each of the students. And now we have our first example here already of this lambda function. So maybe we need also a list of students. Maybe vector of students. So, and no more pointers today. Student list. Maybe again me. Have you ever existed during this practicals? Now
No.
you exist. Okay. So
Yeah.
yeah. So
Maybe do you want to show us now how you can call the lambda function just so?
for one student.
Yeah.
Okay. Maybe if you want to call a lambda function for one student, take it and then student list at 0 for, or let it 1. Rid of that.
Yeah. So now the syntax seems pretty weird of this lambda function. We somehow created it as a variable, but yeah, maybe you can run it and we can see, okay,
Without well print.
we just somehow specified the parameters and the return type differently, but we can use it as a function and yeah.
Okay, so this works. Now back to the plan. What I want to do, I want to implement a real function for each. So let's take the real function for each. And we have one parameter, students, and the lambda function. And again, I will write auto because I will not specify the type explicitly here.
Yeah, so what we want to do is call this print student lambda, this function, for every student in this list. And we want to encapsulate this in a function where we can just pass other functions, for example, not print student, maybe upload student, maybe grade student. We just pass in a lambda, and this function should execute this lambda for every student in the list.
So for every student in the list, maybe means we write the for each loop in students. Maybe make it. Do I need? Maybe I also need a const reference here, and we call the function with the student. That's our for each, our generic for each. Iterate over students, call the function. And now, if I call for each, maybe that we can see everything. If I call for each now with the student list and the print student lambda function, then for each element in this vector, we execute the lambda function.
Yeah, so this is a really, you might be familiar in C and ESP with the algorithms with sorting. I think many of you used this in the last assignment, where you passed in a function pointer to a function which then sorted an array for you. And this is just a nicer syntax of how we can do this in C++.
And now we can use this very easily. We can also write another lambda function and call it with another lambda function. And I don't need to even specify it in a variable here. I can directly write it here. So captures, parameters. So it takes a constant student pointer student. It should not return anything. And maybe we just print, just everyone says hello of the students. And now we can also pass this lambda function here.
Yeah.
And if I call it now, then we have first the for each with the original lambda function, and then the hello lambda function is used.
Maybe you can also omit the return type because we just return void.
Yeah, in this case, I think it shouldn't matter.
Yeah.
Yeah, in this case, so the return type is not so important in this case.
Yeah.
But we can also do it like this. And now, of course, I mean, now we just printed something and okay, but you can do much more complex stuff here. So if we don't have, for example, a const student reference here, but just student reference here. We could, for example, modify each student here in the
Lambda
list.
body.
Yeah. In this case, maybe we should not iterate with const here, but maybe we could say, okay, let's say we don't have setters for the students, right? But now maybe we're over the time, but maybe we could change the name, for example, of each student. So we could call here, I don't know, string, the name of the student is then student.getName. And then maybe we say, maybe make it a bit better syntax here, better formatting. We can do something like name plus equals, or say string, no, name equals OOP1 plus name, and then student.setName. Yeah, don't have a setter, but we could do something like this. Yeah, we can do kind of arbitrary stuff here in the Lambda functions.
So maybe one final remark. You used your auto in the parameters. Please don't do this for any other functions. If you want to use Lambda, write auto here, but do not do this in any other case, because this does something you have not learned yet, and maybe then you will get really complicated errors. And yeah.
So always specify the type except for Lambda functions if you want to use them. So still, why should they be useful? We can do much more with them. We also haven't learned the captures. We will not do today because we're already over time, but we will see this next time. But we can do fancy stuff with this thing here.
Yeah. So I think the concept is easy enough if you get over the weird syntax.
Yeah. Otherwise, it's just a function which is stored in a variable or directly written in the function call.
Yeah, and we can pass them around, return them, pass them to functions.
Do everything which are variables. Okay, and everything else in the Lambda part we will see the next time. Yeah, the main topic today was the smart pointers. We have shown all of the three types: unique, shared, weak pointer, so the implementation of the shared pointer. Yeah, and I think in 10 minutes we will start with the lecture about operator overloading, which I have also mentioned today 2 or 3 times.
Yeah, a very fun topic.
Okay, thank you, and until next week.